Uh, on one hand, I'm a little sad because I gave an online talk almost 2 years ago in a similar seminar. And I'm only sad because that means we've been doing this pandemic thing for almost 2 years, or over 2 years. But on the other hand, I'm very happy. You know, it's nice to get to talk to an audience that I wouldn't have otherwise gotten to see. And so thank you very much for inviting me. Okay, I'll talk a little bit about harmonic analysis techniques for almost minimizers. Let me give you a little bit of talk preview. I know that for a lot of you, it's late at night. This way, you know, if you fall asleep during my talk, at least you'll gotten something out of the talk. So there's this huge branch of mathematics which studies elliptic PDE in rough domains, and it borrows a lot of ideas from free boundary problems. In this talk, we'll talk about a sort of way of giving back, if you will, where people who know things about harmonic analysis and geometric measure theory try to inform the study of free boundary problems. And the basic idea is that we'll be thinking about these things called almost minimizers, which don't minimize a functional, but rather minimize it up to some sort of error. And for almost minimizers, PDE techniques are not available. So you have to sort of resort to these other GMT and harmonic analysis techniques. What's nice is that almost minimizers have some sort of scale and variance to them. And harmonic analysis and geometric measure theory thrives in the presence of scale and variance. And so these tools are easily adapted. So the first half of the talk will be some older results on free boundary and the functional. And then at the end of the talk, I hope to talk about a preprint that will be coming out in the next 2 weeks or so, which will be talking about the branch points of these minimizers. And throughout the entire talk, please feel free to interrupt me with questions, comments, whatever you have. I really appreciate it. Great. So I'll start. So let me do a little introduction or maybe a little bit of review of harmonic measure in the Dirichlet problem. So you have some domain, which you can see here. You pick a point X inside the domain and you run a Brownian motion. And then you keep track of where the Brownian motion first exits the domain, right? Brownian motion is transient, so it will exit the domain with probability 1. And then the harmonic measure with a pole at X of a subset E of the boundary is simply the probability that this Brownian motion first exits the domain in E. You might ask, who cares? The answer is that this harmonic measure is also connected to the Dirichlet problem for the Laplacian. So if you're looking for a function u, which is equal to some function f on the boundary of your domain, and which is harmonic on the interior of your domain, you can find u at x by integrating f over the boundary against the harmonic measure with a pole at x. So physically, this means that if you know the harmonic measure, you can test an electric field on the boundary of a metal plate and understand exactly what the field's value will be at any interior point on this electric plate, right? Which could be a sort of weird shape, as you can see in the picture. Cool. Here's a nice picture I stole off Wikipedia. So why do you care about harmonic measure? Because you care about quantitative well-posedness. So the idea is that if you're trying to solve this boundary value problem, u equals f on the boundary, u is harmonic in the interior, you want small changes in the LP norm of f to result in small changes in the LP norm of uf. When p equals infinity, this follows from the maximal principle, right? But when p is not infinity, this is actually quite difficult. Basically, the entire field of Fourier analysis is built around answering this question when p equals 2 on the disk, right? But if you don't have the disk, you can't separate variables, you can't use a Fourier series representation of the harmonic function, it becomes much more complicated. But quantitative well-posedness is important, right? If you care about applications, if you care about numerical simulations, or even just from a pure theoretical mathematics perspective. It's sort of harmonic analysis 101 that if you have quantitative well-posedness, u of f is really equal to f on the boundary in the sense of suitable limits, right? This is slightly complicated because f might be defined almost everywhere as opposed to everywhere, so on and so forth. And so basically 100 years of tough mathematical research has shown that if omega is a good domain, then we have quantitative well-posedness of the Dirichlet problem if and only if harmonic measure interacts nicely with surface measure. So I use the sigma here to talk about surface measure on partial omega, which is the domain. And if you know what a infinity weight is, that's great. And if you don't know what an A infinity weight is, it's some measure of quantitative mutual absolute continuity. And so what's the big question? What conditions on omega imply that the harmonic measure is one of these nice weights, has a nice relationship with the surface measure? There's been tons of work on this, literally over 100 years of really tough work. In 2 dimensions, it's related to complex analysis. There's relations to other elliptic PDEs, but we don't have time to talk about everything. I really want to talk about 2 highlights. One is a theorem of Guy David and David Jerison, which says that if your domain is quantitatively open and connected, there's a technical term called NTA, and its boundary has quantitatively n-1 dimensionality. The technical term is AHLFORS regular, but you can just think of basically any domain given by a smooth graph on the boundary or piecewise smooth. Then we have this nice property. Harmonic measure is quantitatively mutually absolutely continuous with respect to surface measure, and you can quantitatively solve the Dirichlet problem in LP. More recently, Jonas Azam, Steve Hoffman, Chema Martel, Mihalis Morgoglu, and Xavi Tolsa in a paper in Invenciones gave a sharp characterization of domains in which this problem is quantitatively well posed, in which the harmonic measure is mutually absolutely continuous with respect to the surface measure. And this ended or answered a 100-year-old question posed in 1919 by the F and M Rees brothers. So this is a really big result. Let me try to relate these results to free boundary problems, which maybe as a group you're a little bit more familiar with. So let's recall that the Green's function is a positive function in omega. It has a pole at some point x, which we decide. It's 0 on the boundary, and the Laplacian of the Green's function is equal to the Dirac delta. Sorry, this should say Dirac delta at x. So what's the example that you know and love? If omega is Rn and x is the origin, then g of x of y is some normalizing constant times x minus y to the n-2, right? The fundamental solution of the Laplacian. But of course, these Green functions also take into account boundary conditions, right? So they're more interesting when omega is not the whole domain, but rather just a part of a domain. Great. If the boundary of the domain is smooth, we can actually write down the relationship between harmonic measure and surface measure. It's simply the normal derivative of the Green's function at a point. If you've seen this object before, you've probably seen this object before. It's often called the Poisson kernel. Sorry, my handwriting is not very good, but you're supposed to stop me and ask me questions if you have them. So hopefully you'll ask if you can't read something. Here's the Poisson kernel. Right? So when we're specifying harmonic measure, we're specifying Dirichlet and Neumann conditions. We have some domain, partial omega. We have that Laplacian of G is basically equal to 0, right? Because we can think of the pole as being really far away. So X is somewhere up here. And then on the boundary, we say that G equals 0 and d nu of G is nice. Since we're over-determining the problem, it means that omega can't be anything. There has to be some constraints on omega. And thus this turns into a free boundary problem, right? And so the big question is, if we know that this Radon-Nikodym derivative, this Poisson kernel is nice, can we say something about the domain being nice? And for those of you who have worked in free boundary problems, this should feel very familiar. Cool. wonder if there's any questions at this point. Okay, I'll keep going. So let me switch gears to an actual free boundary problem. Alt and Caffarelli in Crelle in 81, and then a little bit later, Alt-Caffarelli and Friedman in the Transactions of the AMS in 86, were the first to mathematically rigorously study a free boundary problem, which actually had been observed, especially in fluid flow, for a very long time. So the idea is that you have this energy functional. The first term is the Dirichlet energy, which you like. And then these terms weight the characteristic functions of the positive and negative sets. So basically, we're trying to minimize the Dirichlet energy versus how large the set is, positive and negative. So these terms want you to get to 0, and this term wants you to be constant. And so the two terms fight against one another. Doing sort of standard variations now, you have to be a little bit careful because this functional is actually non-differentiable, right? These terms are not even continuous if U is in W12. You can show the following, that when U is positive, Laplacian U equals 0. When U is negative, here, let's do this, Laplacian U equals 0. And then there's a condition on the free boundary of U. And that condition basically balances the normal derivatives of U plus and U minus. So it basically says something like d nu of U plus squared minus d nu of U minus squared is equal to Q plus squared minus Q minus squared on the part of the free boundary which intersects both the negative and the positive phase. So this boundary of the positive or the negative phase is called the free boundary because it's not fixed, it depends on the function. And since you have this very nice equation in the domains of positivity and negativity, it's not that hard to see, right? It's basic elliptic regularity that if you can show the free boundary is smooth, you're able to show U is smooth. And more generally, if you understand the free boundary, you understand everything about U. Great. So what's the idea here? The idea is that the positive and negative parts of U should somehow be close to or related to the Green's functions of these domains, the domain where U is positive and the domain where U is negative, right? We could call this like omega plus and omega minus. So that's the relationship between these two types of problems. Great. Okay, so the ideas of Alt-Caffarelli and Alt-Caffarelli-Friedman have been used a ton to study free boundary problems for harmonic measure. There's beautiful one-phase work of Carlos and Tatiana from the early 2000s and late 90s, where they show that the oscillation of the Poisson kernel controls something about the regularity of the domain. A little bit of shameless self-promotion in my PhD thesis. I showed a very similar result, but in the parabolic setting. So talking about something called caloric measure, which has to do with the heat equation. This paper I talked about before by Jonas, Steve, Chema, Mihalis, and Chabi used something called the Alt-Caffarelli-Friedman monotonicity formula in a very important way. And that, of course, was developed in this paper that I talked about before by Alt-Caffarelli and Friedman. In fact, this monotonicity formula has been used a lot, especially in two-phase harmonic measure problems. So when you have two domains that touch one another. Here are some results which I've just sort of listed off, more recent, and then a really beautiful result recently published in the Annals of Math by Ben J, Chavi Tolsa, and Michela Vila, resolved Carlson's epsilon squared conjecture, which was a huge question in harmonic analysis and complex analysis, using this Alt-Caffarelli-Friedman monotonicity formula from free boundary problems. So what's the upshot? It's that we who work in harmonic measure and GMT owe the free boundary communities a lot. We're in a deep debt. And so the point of this talk is we're going to try to slowly repay this debt. We're not going to be able to repay it completely because we're playing 40 years of catch up, but we're going to try to do a little bit. Great. So before we give back, we need a couple of definitions. Recall, this is the functional we care about. And let's do a definition. U is a minimizer of J if for every ball inside the set and for every competitor, which is equal to U outside of the ball, we have that the energy of U is less than the energy of the competitor. Right? This is a standard definition of minimizing in the calculus of variations. But we want to consider something called almost minimizers. So in almost minimizers, there are two parameters, C and alpha. And we say that U is a C alpha almost minimizer if for every ball and every competitor which is equal to U outside of that ball, J, the energy of U, is less than the energy of V up to some error. And this error decays faster than the energy of J in the ball. So you should think of J restricted to the ball as being roughly of the order, the radius of the ball to the n. Right? So this error is going to zero faster than that, n plus alpha. Right? Of course, it's important that it's the same C and the same alpha for every ball and for every competitor. So this little error here can represent a lot of things. It could represent an error that you make in your measurement. It could represent a functional with lower order terms. These things show up a lot. So let me give you a concrete example. If you take the original functional, here I'm letting Q minus be 0 and Q plus be identically equal to 1. And then I add a lower order term. This J tilde will be an almost minimizer in the sense of this definition. Minimizers of J tilde will be an almost minimizer to the original J in the sense of this definition. Right? And that's because this term scales faster than the other terms, right? You can see there's no derivatives here. This particular J tilde shows up a lot in eigenvalue optimization problems. So it's kind of an important thing. Great. So let me try to motivate almost minimizers a little bit more. And then maybe I'll stop because people will have some questions. There's a lot of natural applications of almost minimizers. As I mentioned, lower order terms in the functional. They show up a lot in constrained minimization. So you're on some sort of manifold and you want to understand what's the domain of area 10 with the smallest first Dirichlet eigenvalue. You can write this as an almost minimizer to the Alt-Caffarelli functional. So here are some nice recent results which have exploited this connection. It also shows up a lot in quantitative stability. For eigenvalue problems, you can try to prove quantitative stability by looking at essentially almost minimizers or minimizers with lower order terms of these Alt-Caffarelli functionals. I should maybe point out that almost minimizers were first considered by Almgren in the 70s for the area functional. And there they show up a lot in partition problems, constrained optimization, so on and so forth. There's also some philosophical reasons why you might care about almost minimizers. As I said before, almost minimizers don't satisfy an equation because you just have an inequality up to an error as opposed to an inequality. You can't take the first variation, which means you don't get an Euler-Lagrange equation, which means you can't use PDE methods. So in particular, this allows us to focus on the variational characterization of minimizers, what you actually get out of the minimization as opposed to the PDE, right? So if I can be controversial for a second, and maybe I should wait until I have tenure, but we're all friends here. DeGiorgi-Nash-Moser is incredible, right? It allows us to study the calculus of variations using PDE. But in some sense, it's such a powerful tool that it's blinded us, right? We first always go to PDE methods when we study problems from the calculus of variations. And sometimes the variational characterization is actually more important than the resulting equation we get out. So almost minimizers allow us to sort of get back to the basics. This is particularly useful for problems with messier equations, for example, non-local free boundary problems. I have some joint work for non-local free boundary problems, which uses these sort of variational techniques. And notice that our original function J, right? J is equal to the Dirichlet energy plus, let's say, the characteristic function of where U is positive. This is the simplest version. This is not a convex functional. Again, this term is not even continuous. So you should expect this functional to have critical points, which are not minimizers, things that satisfy the Euler-Lagrange equations that don't necessarily minimize the functional. So if you want to understand how to distinguish between critical points and minimizers, and there's a lot of physically relevant reasons why you should do that, right? If you're modeling something in nature, only stable solutions should show up, not just arbitrary, unstable critical points. So if you want to understand the minimization property, almost minimizers are a good way to make sure that you're focusing on minimizers as opposed to critical points and minimizers. Great. So maybe I'll stop here just for a second, take a drink of water and coffee, and maybe people have questions. It's early here in the Midwest, so it's still coffee time. Okay, if there are no questions, I guess I'll keep going. So let me now give you some actual theorems, some actual regularity results, right? Because I've been talking sort of philosophy for too long. So the results of Alt-Caffarelli and Alt-Caffarelli-Friedman say that if you have a function U, which minimizes your energy, that function is going to be Lipschitz and non-degenerate. What does non-degenerate means? It means it grows at least linearly, right? So U of X is going to be at least on the order of the distance between X and the zero set of U. Furthermore, these functions are C1 beta in the sets where they're non-zero. Of course, they're not even C1 across the free boundary, right? Because if you have a function which is identically zero here and harmonic, but not identically zero on top, the gradient can't vanish at the free boundary by, say, the Hopf maximal principle. So that means that you can't be C1 across the free boundary. And then some very nice work by Guy David and Tatiana Toro way back in 2015. This was the first work to study almost minimizers for these particular functionals, says that the same basic regularity of the function is true for almost minimizers, right? So we had it for minimizers, and now it's also true for almost minimizers. And then more recently, joint with myself and Mariana, Smit, Vega, Garcia, we've shown that this theorem works for almost minimizers with variable coefficients. And I bring this up because it's part of a larger idea, right? That if you have a perturbation of the original functional, right, instead of having just the Dirichlet energy here, you have some sort of Holder continuous matrix. Somehow, almost minimizers should be robust under these types of perturbations, right? I told you earlier that they're supposed to represent some sort of measurement error, lower order terms. And so this was like a proof of concept paper to show this robustness under these perturbations. Cool. So I really want to focus on this idea of compactness, which I mentioned briefly on the previous slide, but I didn't say out loud. It's really quite an important tool. The idea essentially is that when you take a limit of almost minimizers, you get an almost minimizer. And when you take a blow up limit, when you zoom in on an almost minimizer, you get an actual minimizer. So let me try to show you what's going on with the second idea. Imagine you have some sort of curve here's u, which is an almost minimizer to j of u grad u squared plus, let's just do the one phase problem, right? And then you take some points here. This is your point x naught, and here's some radius r. You can define u of x naught r as, at a point x, as u of rx plus x naught over r. This Lipschitz rescaling is the natural rescaling of the problem. And then it turns out that if j of u is less than j of v plus c r to the, oh, maybe I should write c rho to the alpha plus n, then j of u x naught r is less than j v x naught r plus c r to the n times rho alpha plus n, where this is all happening in some ball of radius rho, right? So what am I trying to say? I'm trying to say, as you zoom in, you get another almost minimizer, but with a constant c, which is going to 0, right? And what does this zooming in correspond to? Geometrically, you turn this ball centered at x naught with radius r into a ball centered at 0 with radius 1. So this idea tells you that you should have some hope of getting a nice regularity theory for almost minimizers, because at first order, when you zoom in, you recover a minimizer of the functional, right? As r goes to 0, this term goes to 0. And thus, in the limit, if you can take a limit formally or something like that, you should expect the limit of these u x naught r's to be a minimizer to the functional j, as opposed to an almost minimizer. This is a very nice idea. Cool. So with this idea in hand, we can actually prove nice results on the regularity of the free boundary. So seminal results by Alt-Caffarelli in this aforementioned paper say that if you're in the one phase problem, right, so q minus equals 0, minimizers satisfy what's called a flat implies smooth result, or an epsilon regularity result. So in particular, you can write the free boundary as two pieces, a regular part and a singular part. The regular part is going to be open, dense, and locally given by the graph of a C1 beta function. So it's going to be a smooth graph almost everywhere. The singular set is small. It's going to have Hausdorff dimension less than, say, n minus 3. The precise size of the singular set is actually one of the biggest open problems in this area. This is a common characterization of minimizers to variational problems. For example, in minimal surfaces, the famous Simon's cone tells you that if you have a minimal hypersurface, it's smooth almost everywhere, and the set of points where it's not smooth is a set of codimension at least 7. So, work with Guy David and Tatiana Toro way back in 2019, we showed the same regularity result for almost minimizers to the one face, right? So we're saying that to first order, almost minimizers satisfy the same regularity as minimizers of the problem. So this is the best possible result we could have hoped for. And key to this result was a harmonic analysis GMT lemma. So it made me very happy. We say, imagine you're an almost minimizer even to the two-phase problem. Then the positive and negative sets are quantitatively open. They're quantitatively connected. I'll talk about what that means in a little bit. These are called NTA domains. And the boundaries are quantitatively n-1 dimensional. People call this AHLFORS regular or AHLFORS David regular sometimes. So basically, this was the essential starting step to proving our main theorem. And I really want to emphasize this. We didn't prove this theorem just because we could, or because, you know, we wanted to pump up geometric measure theory and harmonic analysis, you really need to start with this in order to start implementing the types of techniques that you would imagine would be involved in an epsilon regularity result. Okay. So let me try to give you some ideas of the proof of this theorem. In particular, let's talk about quantitative openness. So what does quantitative openness means? It's a condition called the corkscrew condition. This name was invented by Carlos Koenig and David Jerrison, presumably over a bottle of wine sometime in the 80s. And it says the following: take any point on the boundary of the domain. There exists a point in the interior and the exterior of the domain at scale R, and these points are not too close to the boundary. So this distance is bigger than M inverse of R. So basically, this rules out cusps, either going in or out of the domain. Okay? And it turns out that being quantitatively open basically follows from being Lipschitz and non-degenerate, from not growing faster than linearly and not growing that much slower than linearly either. Now let's talk about quantitative connectedness. This is known as Harnack chains. It's an important PDE concept. And basically it's saying, here's my domain. If I have 2 points in the domain, I can connect them with a chain of balls. The balls stay far away from the boundary and there's not too many of them. And you can already see why this would be useful, because if the balls stay far away from the boundary, you can enlarge them a little bit, and then you can apply the Harnack inequality multiple times to compare the value of U at this point to the value of U at this point, if U is harmonic and positive. So this is sort of a quantitative connectedness, right? You can like draw a path that goes through the center of these balls. And we're basically saying that any 2 points can be connected by a path that's not that long and doesn't get too close to the boundary. The key observation in proving this is that if you're a minimizer defined on all of Rn, you have to have connected open sets, or sorry, connected positive and negativity sets. And so basically we use a compactness argument to show if, let's say, the positivity set of some sequence U sub I, a sequence of almost minimizers. If we use a positivity, if we have a sequence of these positivity sets, and if they're getting less and less quantitatively connected, then in the limit, they'll converge to a minimizer, converges to a minimizer, which is globally defined, not connected positivity set. Have less and less connectivity. Of course, I'm being a little bit vague with this whole thing, but I hope you get the vague idea, right? So again, these important theorems are using ideas of compactness and scale invariance, and so on and so forth. Cool. Let me talk about AHLFORS regularity a little bit. Let's see if I can define it. So let me give you a definition. Mu is D AHLFORS regular if there exists a C bigger than 0, such that for all x in the support of mu, mu of B XR acts like R to the D. So for example, surface measure supported on a smooth D-dimensional manifold is D-AHLFORS regular. But there's lots of D-AHLFORS regular measures which are not regular in the sense of being smooth surface measures. So for example, if you take a four-corner Cantor set, right, and then iterate this over and over and over again, you can show that the length measure restricted to this Cantor set is 1 AHLFORS regular. So AHLFORS regularity is important. It gives you some sort of quantitative dimensionality, but it's not quite equivalent to being smooth. And basically what we do is if this is the free boundary of our minimizer, we use results from harmonic analysis and GMT, in particular this result of Guy David and David Jerrison that I talked about many slides ago, to show that the harmonic measure, right? So I should say harmonic measure of this domain is n-1 AHLFORS regular. And that's what allows us to show that the domain itself is an AHLFORS regular domain. And that's an important part of our regularity. Okay, so I got into a lot of details there. Maybe I lost some of you. This is a good place to reset because we're about to start talking about something else completely. So let me just take a sip of coffee and maybe people have questions about the last couple of slides. Okay. So if you're observing, if you haven't fallen asleep yet, you'll notice that the past couple slides, I gave these definitions for the one-phase problem. And in particular, my paper in advances with Guy and Tatiana only treats Holder regularity for the one-phase free boundary problem. And the question is, what about two phases, right? These basic regularity results for connectivity and AHLFORS regularity apply to two phases. Why can't you get Holder regularity for the two phases? And the problem is cusp points. So here's a very nice picture from a very beautiful paper of Guido Di Filippis, Lucas Bolaro, and Božidar Velichkov. And the idea is the following. There's a different free boundary condition on two-phase points, points where the positive and negative set come together, than there is at one-phase points, points where the positive set touches the zero set or the zero set touches the negativity set. But if you're at a cusp point, a branch point where the two free boundaries come together, right here, then you can look like a two-phase point at one scale, but when you zoom in, you start looking like one-phase points, right? So here, these two phases are really close together, but when I zoom in, the two phases come further apart. And so handling this transition between one phase and two phase is really quite difficult. And it stymied researchers working in this area for a very long time. So, for the one phase problem, regularity was established by Alt-Caffarelli in 81. For the two phase problem, if there are only two phase points, so no branch points, Alt-Caffarelli and Friedman understood the regularity. And then Daniela da Silva and her collaborators in the mid-2000s gave us a much deeper understanding of that regularity. But still, missing was the transition from one phase points to two phase points, the understanding of branch points. Missing until recently, because this beautiful paper of Guido, Luca, and Bojo in Invenciones in 2021 proved the regularity theory at these points. It basically proved that these two curves, the positive curve and the negative curve, come together as C1 alpha graphs with mutual tangency at these branch points. If you know anything about minimal surfaces, you know that in higher codimension, minimal surfaces can experience similar branching phenomena. And this is similarly very difficult to understand. I think we only really understand it in the actual surface case. So when the dimension of the minimal set is 2. But if you have like a 3-dimensional minimal surface in R5, for example, we don't know anything about what the branch set looks like, or we know very little. Cool. So this is a beautiful paper by Guido, Bojo, and Luca. But it begs a very important question. Can you actually write down an example where the free boundary looks like this, where the free boundary has a cusp set, right? It's not so easy to do. It's quite easy to construct examples with only 1 phase points or no 1 phase points. For example, you can build a sort of box, and then if your Dirichlet values look like 0, 0, positive, negative, then your minimizer is going to look like this. And the 2 phases will never come together. And then if you're a little bit more careful, you can actually build a minimizer where U is positive here and U is negative here. But there's no sort of splitting, right? So the question that we're basically asking is, can you build a minimizer which looks like this? So this is the positivity set, this is the negativity set, and this is where U equals 0, right? Does this exist? Because if it doesn't exist, well, then the paper of Bojo, Luca, and Guido is very nice, but it's a little bit unnecessary, right? So there's a very nice preprint, again, by Bojo, Luca, and Guido, which came out just last fall, which produced critical points that exhibited this branching phenomena, right? So critical points that look like this in dimensions 2, using quasi-conformal mapping. Gorgeous idea. And in fact, they prove a structure theorem for these branch points, these points where the free boundaries come together. But again, this relies on quasi-conformal mapping. It only works for critical points, and it only works in dimension 2 because it's a complex analysis technique. Still, it's a very nice paper. So in an almost preprint with Guy, Mariana, and Tatiana, I say almost preprint because it should come out any moment now. We can construct examples of minimizers to the functional J, where Q plus and Q minus are equal to 1, which exhibit branch points in dimensions 2 and 3. So what does this look like? Our functional is this. J of U is the Dirichlet energy of U plus the size of its positivity set plus the size of its negativity set. And we construct a domain, which is a long, thin box, and boundary values on the top and the bottom of the box. So maybe I'll call it F plus and F minus, such that the minimizer to this functional, which achieves these boundary values, has the following shape. So here U is equal to 0, here U is positive, and here U is negative. And so in particular, there are 2 nice branch points here and here. And we're actually able to show more. We're able to show that outside of this sort of interior box, there's only 2 phase points. So you have 1 phase points inside and 2 phase points outside. So we can actually construct these examples. Great. So this shows that we haven't been wasting our time, that understanding branch points is important because they actually do show up. So I think I have some time. So let me try to give you some ideas on how this proof works. You might think that we construct the minimizer explicitly, but this is actually really hard to do. There are essentially no tools in the free boundary community where if I give you a function, you can verify explicitly to me that that function is a minimizer. So instead, we say, okay, we can't construct the minimizer explicitly, but we come up with boundary values. And basically, these boundary values are close to 1, and then they pop up, and go back down and close to 1. So at the sides of the box, you would expect the function to look kind of like, so this is 1 and -1. You expect the function to look kind of like y here, right? So you expect u of xy to look kind of like y at the sides of the box because it would achieve the boundary values and it's harmonic. It's very nice. And in the middle of the box, you expect the function to have some sort of pool of zeros, right? So the idea is that we construct these boundary values so that if you minimized slice by slice, you really would look like something like this. Of course, you can't minimize slice by slice. That ignores the energy going in these directions. But then we use a bunch of harmonic analysis and geometric measure theory tools, very similar tools to the previous theorems that I talked about, to show that the slice by slice minimizer constrains the behavior of the actual minimizer. And that's what allows us to show that this pool exists. If you're interested, the preprint should be coming up anytime soon. So let me sort of end by talking a little bit about some open problems, which I think are really interesting and important in this area. We want to understand not just the existence of these branch points and the regularity of the free boundary around these branch points, which now we both understand, thanks to work of Boja, Luca, and Guido in this upcoming preprint with Mariana, Guy, and Tatiana. We also want to understand the structure of the branch points. Can there be a lot of branch points? For example, can your free boundary look like this, where you start to have a bunch of branch points accumulating at some other point here? Studying minimal surfaces suggests that the branch points shouldn't be too large. In particular, the branch points should be contained in an n-2 dimensional manifold. Okay? So basically it's saying no to this picture where I showed you an accumulation of branch points. Right, because here n equals 2, so an n-2 dimensional manifold is a 0-dimensional manifold, which means I should just have isolated points. They're not allowed to accumulate. You know, again, this is the positivity set, this is the negativity set, and inside these little pools, u is equal to 0. Understanding the analogous conjecture in minimal surfaces is a really big open problem that lots of people are working on. In the free boundary world, this conjecture was confirmed by the aforementioned preprint when n equals 2. But it's wide open when n is larger. In particular, the n equals 2 confirmation relies on analyticity because it's a quasi-conformal thing. So even when q plus and minus are not analytic, this is an open question and n equals 2. To be honest with you, we thought about this problem for a while, trying to prove structure for the branch points. We didn't know what to do. It was too hard. So we thought, can we say something about almost minimizers, the branch points of almost minimizers? And so in this same almost preprint, which is coming out soon with Guy, Mariana, and Tatiana, we show that almost minimizers have no structure on their branch points. So you pick any set you want, any closed subset of Rn-1. I can come up with an almost minimizer U such that the branch points to U lie exactly in the set E. Okay, so I have to be a little bit careful. E has to be the boundary inside of Rn-1 of some other set O, but fine. Right, and O is inside of Rn-1. So what I'm telling you is, you know, pick some fractal, something weird. Maybe it looks like a snowflake here, all living inside of the page. I can pick it so that I have an almost minimizer to this functional, and the positive set and the negative set of these almost minimizers come together at exactly the red points that I've outlined here. So there's no structure to the branch points. They certainly don't live in an n-2 dimensional C1 manifold. So this theorem for minimizers is still a big conjecture, a big open problem. I think you should all work on it. But for almost minimizers, the answer is clearly no. Almost minimizers are too flexible. And this is kind of interesting, right? We showed you earlier in this talk that almost minimizers have the same first order behavior as minimizers. But this shows you that if you look at higher order behavior, almost minimizers and minimizers are very different. Okay. Let me just say something very quickly about these almost minimizers. The key idea is as follows. So there's this very nice paper of Guy, Joseph Fenoy, who's a postdoc, working with Bojo, and Svetlana, maybe Rhoda, where in a completely different problem, studying higher codimensional harmonic measure, they introduce what's called a regularized distance, which is d alpha of x. You integrate over some set omega, x minus y to the d plus alpha to the -1 over alpha. So here alpha is positive, gamma is d-dimensional, and x is in Rn minus gamma. What they show is that d alpha is basically a smoothed out version of the distance function to gamma. And we observe that d alpha is an almost minimizer. To J. For all nice gamma. So basically, we pick the boundary of the positivity set, the boundary of the negativity set. Since we could pick them to be any C2 graphs, they can come together in really nasty ways, right? A C2 function can vanish on essentially any closed set. And then we build almost minimizers using these regularized distances, which showed up in a completely different context. We build almost minimizers exactly so that their positivity and negative sets have the boundaries that we want. Okay, I think that's all my time, and you've been extraordinarily patient. So thank you so much for your attention, and I hope you have a great rest of your day.